lemma and studied was this lemma. Let X be a non-linear space. So B of X is an algebra with identity. When we say that B of X is an algebra, it means that B of X is a vector space with dot operation or multiplication operation. Here the multiplication T and S is the combination of X and T and S. Notation. Let X be a normal space and let T be a bounded linear transformation on X. So when we write T means the combination of T with itself, we denoted this by T power 2, and T will be denoted by T power 3 and etc. So T power n is the composition T with itself n times. B. If A0, A1, An B in F means they are scalars, and P from F to F B is the polynomial defined by P of X equals A0 plus A1x plus Anx power n. So we can define P of T by P of T equals A1I. I means the identity function. A1T and ANT power n. So we replace T by X, and we can define P of T by this formula. Let me see if everything is okay. Okay. Lemma. Let X be a non-linear space and T be a bounded linear transformation, or T belongs to P of X. If P and Q are polynomials and lambda and mu be complex numbers, then lambda P plus mu Q of T equals L P of T plus mu Q of T, and PQ T equals PT composition with QT or product multiplication with QT. Some exercises. Inverse operation. When we write AX equals Y as a matrix equation, it means that A is a matrix and X and Y are two matrices. So if A is invertible, we denote the invertible of the matrix A as A power minus 1. So from this equation, with the inverse of A, we can write X equals A minus 1 Y. Here if we call A as an operation, A minus 1 is the inverse of the operation A. Definition. Let x and y be nonlinear spaces, and operation T belongs to B of x and y. It means that T is a bounded linear transformation from x to y, is said to be invertible if there exists another operation S belongs to B of y and x, such that the combination of S and T equals Ix, means the Ix I wrote here. Ix is identity function from x to x, such that Ix of x equals x for all x in vector space x. And Ts equals Iy. You see, Iy is a linear transformation from y to y, and this is identity function. In this case, we say that T is invertible, and the S is called the inverse of T and denoted by T minus 1. By the lemma, if T as a bounded linear transformation from x to y is invertible, the inverse of T is unique. So any invertible operation can have just one inverse, not more than one. Another lemma: let x, y, z be nonlinear spaces, and T1 belongs to B of x and y, T2 belongs to B of y and z, and they are invertible. So T1 minus 1 is invertible too, with the inverse T1, and the composition of T2 T1 is invertible with the inverse like this. You see, in the inverse of this operation, the place of index are changes. Here T2 T1, but T1 minus 1 T2 minus 1. And for invertible bounded operator T, we remember that T of n is the composition of T with itself n times. So if T is invertible, the invert of T power n is denoted by T power minus n, and is the minus 1 of T power n. Definition. Let x and y be nonlinear spaces if an operator T exists, then x and y are isomorphic, and T is called an isomorphism between x and y. So we say that two vector spaces, linear log spaces, are isometric. There is an invertible linear operator belongs to B of x and y. It is easily to see that if T is an isomorphism, then T minus 1 is an isomorphism too. Lemma: if the non-linear space x and y are isomorphic, then we have if dimension of x is finite, if and only if the dimension of y is finite too. So if one of these vector space has finite dimension, the other must have finite dimension, and then they have the same dimension. Dimension of x equals dimension of y. X is separable if and only if y is separable. So if two non-linear spaces x and y are isomorphic, if one of them is separable, the other must be separable too. X is complete or Banach if and only if y is complete or Banach. We can ignore this example and left it for your personal study. Theorem 4.40. Let x be a Banach space and T belongs to B of x, means T is a bounded or continuous linear transformation on x. If T belongs to B of x is an operator with the norm less than 1, then I minus T is invertible. I means the identity function from x to x. When the norm of x is less than 1, then I minus T is invertible. And the invertible of I minus T is the series T power n from 0 to infinity. Notation. The series in the previous theorem means this series, It is called Newman series. So Newman series means a series like this: T over n from 0 to infinity. Okay. We pass from this example. Corollary. Let x and y be Banach spaces, then the set A of invertible operators in B of x is open. like this. We have x and y. And A is such a subset of B of x and y. A such that all members of A are invertible. A, the subset of B of x and y is open. So A is an open set in B of x and y. Another theorem. This is a very important theorem. Important and famous. Important. Important. This theorem is called open mapping theorem. Open mapping theorem. Suppose that x and y are Banach spaces and T be a bounded linear transformation from x to y is surjective. Surjective means onto. So the range of T must be y, the whole y. Let L be the set of T of x for all x such that the norm of x is less than or equal 1. And we denote the closure of L bar. Then A. There exists a real positive number R such that the set of all y with the norm of y less than R is in L bar. The set of all y such that the norm of y is less than or equal R over 2 is in L. Or this set is a subset of L. If in addition or furthermore T is 1 to 1, then T is invertible. So T is surjective, and if T is 1 to 1, so T is surjective and 1 to 1, and so T must be invertible. This is a famous theorem in functional analysis called open mapping theorem. We should wait until the internet becomes stronger. It is weak now, so I can continue. Okay. Oh. Oh. Crowley. Another theorem that is really important uh, important is the close graph theorem. This is a Crowley of open mapping theorem, and it says that if x and y are Banach spaces and T is a linear transformation from x into 1, then the graph of T, g of T, graph of T is closed. If the graph of T is closed, then T is continuous. We can use this term like this if we have a sequence xn and the of x equals yn. So we have we have a double sequence xn and yn. If we say b closed, if xn approaches y, then and tx is y, then t is continuous. Another theorem that is the Crowley is Banach isolation. This theorem says that if xi spaces and T a linear transformation from is objective on 1 to 1, then is invertible. Other x and y are non-linear spaces and T belongs to V of x and y is invertible, then only have the norm of T of x is greater or equal the norm of T minus 1 minus that the norm of x. Okay, suppose that x is multi space and y is a normal space and T belongs to V of x and y. If there exists a positive alpha such that the norm of x is greater or less than alpha of x for all, then the theorem. Suppose that y are and t y, the following are equivalent. A. Invertible. B. The image is dense y and there exists a positive alpha such that the norm is greater or equal alpha dot norm of x for all x in x. Suppose that x and y are bounded spaces and T be a bounded transformation from x. Then the operator T is not invertible if and only if the image of T is not dense in y, or there exists a sequence xn in x such that the norm of xn equals 1 for n, but the limit of T of xn equals 0. Example, for any in 0 and 1 means the whole function from 0 and 1 to c, continuous function from 0 and 1 to c, and let h be a member of B of L power 2 0 1 is defined by a formula that is 4.3. If F is a member of C and 1 is defined by F of 1, F is invertible. This is also an important theorem, boundedness principle, uniform boundedness principle. This theorem is that if U and X be bounded spaces and is another set, and for each S, T of S belongs to V of U and X. If for each in U, in capital U, the set of all instead of the normal Ts of U for all S in S bounded, then this set is bounded to. Another way, let U and X be Banach spaces and Tn belongs to X for n from 1 to 3 and etc. And suppose that limit of Tn and define Tu limit of Tn when n goes to infinity, then T must be a bounded due to now we can deal with the duality of Banach and another very important theorem in function analysis. But I think it's enough for today. We will start this section next time, and because if I continue, I should start a new concept and it may be difficult for you. So I think it's better to stop teaching here, stop lecturing here. Okay. This week we have just this session for lecturing, and Tuesday we don't have lecture, and the next lecture will be Sunday next week. So we will study this section next week Sunday, inshallah. If you have any question, I will at your service. Any question? Okay. And remember that the class will be, so please enter the class on time. The next session will be at Sunday afternoon at 3:30. Okay, so bye.